instructions and images in association with the fantastic Derwent Training Association based in Malton, Yorkshire, present shear force and bending moments. This video presentation is for the HND level 4 and 5 in engineering, covering unit 4 mechanical properties and unit 2 engineering science. As you can agree, it's not the catchiest title in the world. We're not going to go to the BAFTAs with it. However, it's what we've got. So by the end of this presentation you should be able to calculate shear force in a beam and draw shear force diagrams. So for my students, if you think you've seen it all before, yep, we covered this in great detail to the nth degree, alright, in Unit 2 Engineering Science. So quickly moving on, alright, we have our self-assessment exercise number 2, which is on page 9 of your booklets that I handed out on Thursday. What we have is a 4 meter beam. It can be made out of anything that you wish, concrete, I-beam, anything. We have a point load of 200 Newton meters, 1 meter in from the left hand edge, and then all the way across the beam we have a uniform distributed load of 80 Newton meters. So this is our problem. Now what we've got to do is, first thing we've got to do is we've got to calculate, right, our uniform distributed load. To do that, what we actually need to do is to make it change, and we change it to a point load. To change it to a point load, you take the force times the 4 meters, alright, which will give us 320 Newton meters. But that's not the whole story. Now what we have to find and have to work out is where we would put the 320 Newton meters. In this case it's quite easy. We have a uniform distributed load moving all the way across the beam. So half or 50% of 4 meters is 2 meters. So therefore right in the center of the beam we could place 320 newtons. However, if we had a uniform distributed load that was moving from the right hand edge to the left hand edge, or the left hand edge to the right hand edge, and it was only, say, 3 meters long, you would have to half the distance of the entire uniform distributed load. So therefore if it's 3 meters long at 1.5, you would then put the 320 newtons. So don't always take it for granted that you just bang the uniform distributed load straight in the middle of every single beam that you come across, because that's not the case. So first thing we've got to do is we've got to do or calculate the moments. Seems a bit odd, but we're calculating for the right hand side first. So therefore you have the sum of the moments and the length. So what I've done is I've color coded it to try and make it a little bit easier. We have red for mass and we have blue for the length. So therefore first point we come across, we have 200 Newton meters at 1 meter inside our beam. So therefore 200 times 1, that gives us 200. Moving across, at 2 meters in we have 320 newtons. Times that by 2, that gives us 640. Now what we would do is we'd minus the the forces at the right hand edge, and obviously they're times by the entire length of the beam, which is 4 meters. A little bit of transposition of formula, you just obviously divide the 4 by 4, and then you would divide the rest of the equation by 4. So 200 plus 640 divided by 4 will give us our forces acting on the right hand edge of 210 newtons. To work out what is going on the left hand edge, all we do is we add our 200, we add 320 newtons, but then we minus the right hand edge, so therefore minus 210 newtons, which will give us 310 newtons. To put this into some kind of picture, an image that you may be able to memorize better than numbers, things like that, this is the actual shear force diagram for this beam. So therefore this is what I would for my students expect to see if you were doing an assignment, etc., etc. What you do is you draw this to a scale. You choose the scale. Alright, it's not dictated to you. I've just tried to keep it simple, stupid. So everything is in 10 millimeters. So the length of our beam, 1 meter, 2 meter, 3 meter, 4 meter is actually 40 centimeters. Same along the top, 100, 200, 300. So that's our shear force diagram. On the our left-hand edge, obviously we had a positive force of 310, so that's going upwards. And then on our right-hand force, we also had a positive 210. The two have got to meet in the middle. So we've got 230 newtons, minus 50 newtons, minus 130 newtons, and minus 210 newtons. Now the question is, or some of you will be asking, where do you get those numbers from? This is from our chart, which you create as you're creating the shear force diagram. The left-hand edge, we're not moving anywhere, so x is equal to 0. So therefore the force that is acting on the left-hand edge is 310 newtons. If you remember back to the picture, at the top, 310 newtons. Makes sense. We move 1 meter in, so we have 310 newtons minus the uniform distributed load, which is 80 times 1, which will give you 230 newtons, hence where we get the second point. At point 2, 2 meters in, things change slightly. We have our left-hand edge, which is 310 newtons. We minus our point load of 200, because the point load is acting at 2 meters in, minus uniform distributed load, which is 80 times 2. So therefore, what we end up with doing is we end up with 110 newtons, minus the 80 times 2, which will give us our minus 50. Move down to the third meter. Instead of writing the 310 minus 200, etc., we just keep it 110 newtons minus 80 times 3 gives us your minus 130, and then we move on to the final edge of the beam, which is the right hand edge. So you have 4. Alright, 80 times 4, 110, it gives you minus 210 newtons. That number needs to be exactly the same as the force that you found for the right hand edge. As long as those two match, everything's hunky-dory. If they don't match, then somewhere in your calculations you've gone wrong. Alright, there you go. For my students, crack on. There's another self-assessment exercise which I want you to do on your own. You can either submit that onto the Google Classroom or bring it in next week. I'll have a quick look at it. And for the rest of you, okay, this presentation was produced with the help of Tor. Alright, this is where a little camera exercise. Alright, they're part of the Sparkle group, and they also do VideoScribe, which is a really fantastic piece of kit. Check them out at www.tor.co.uk for more. Thank you for watching.